some backgrounds. So let's first consider the space Sk gamma 1n as a space of classical cuspidal modular forms. Of weight k and level gamma 1n. For technical simplicity, I will assume n is at least 5. And so we know that if we are counting with at least 2 model forms, we will know the dimension of this space. You can compute this dimension by the Riemann-Roch theorem.
The reason you chose gamma 1 rather than anything else?
Well, if you choose some other level, this dimension may not be strictly a linear function of k. Yeah, but I just want to say, if you choose this level and you compute this dimension and you fix the level n, you only concern the function as a function in terms of the weight k. This should be a linear function in k by Riemann-Roch. Oh, sorry, linear function. So we try in this talk, we try to generalize this phenomenon to, for example, a quadratic number field. Actually, we can do much better than that, but I just want to emphasize on the case degree f is 2. So in this situation, the space of cusp modular forms are indexed by two integers instead of 1 integer. And yes, I will still fix a congruent subgroup gamma of SL2OF. And I will use SK1, K2 gamma to denote the space of cusp modular forms of weight K1 and K2. And level gamma.
Are you assuming f is imaginary or real or not?
Not
Okay.
yet. Yeah, I will say. I will say now. So there are 2 situations. First, that if f is real quadratic. Shimizu has proved that he has established asymptotic growth of that the dimension of that space. and it is approximately multilinear in both K1 and K2. And this is the case for this constant C depends only on the level gamma.
I'm sorry, but probably I missed something. What do you mean? Weight? I probably missed something. What is weight K1, K2?
Because
what does it mean? I know what is weight K. What does it mean K1, K2?
yeah, so
it's my
general,
ignorance, I guess.
No, it's you should explain it. Yeah, explain it.
yeah, sure. So this case corresponds to the Hilbert modular form case, and so the translation is given by two integers. Like yeah, I will explain this later. Actually, the way I always think about this is by consider a representation of SL2 F infinity. And if you so in this case, for example, in the case of SL2R times SL2R, this representation is given by two in the box tensor of two representations with different index. Yeah, but yeah, I will explain that later in terms of cohomology. Yeah.
Sorry, is it a comma though? I thought it was a product of K1 and K2.
Oh, sorry. There is a comma. It is quite small.
I mean the last line.
Oh, last this line is a product.
That is a
K1
product.
Yeah.
Okay, thanks.
Sure. So then I want to discuss.
Sorry, so what do you mean by level gamma?
Gamma is a congruent subgroup of SL2OF.
But I mean, upstairs, the first example was gamma 1 of n. Is it a particular congruent subgroup you're thinking about, or is it related to a particular ideal?
No, this is only for illustration. This gamma can be.
So it's an arbitrary congruent subgroup.
Yes, yes.
Okay.
I'm sorry, this is a silly question, but so these cusp forms are defined on SL2R cross SL2R? Like two copies of the upper half.
Yeah. So there are
two copies of upper half plane. Yeah.
That's weight K1 and K2 in each coordinate.
Yes.
That's the easy case. In SL2C, he'll explain what this is.
You can also define them on SL2.
Yeah.
His main talk is about SL2C.
Right.
Is this C explicitly computable?
Yes.
Yes.
This is the trace. You can write the trace formula. If you discrete series, you get an exact answer because by a principle that all conjugacy classes except elliptic conjugacy classes don't contribute. And you can also get it from an index theorem.
Yeah. Okay.
Yeah, Shimizu's method is analytic using trace formula.
Okay, great.
Okay, we're left to consider the imaginal quadratic case. Actually, things become much more complicated. For example, this space would vanish if K1 not equal to K2. And this is because these cohomological forms come from unitary representations of SL2C, and there are some classification of unitary representation of SL2C.
A silly question again. So these cusp forms are not holomorphic, what you're considering now.
So in the real case, you can still talk about holomorphic cusp forms, but in general, there's no, in general, for general number field, there's not a notion of holomorphic, but I will talk about it. So I think the correct generalization of holomorphicity should be cohomological, and I will explain what
This is good.
that means.
There's a learning seminar, as Alex always likes to say. Ask away. This is good. So many of us have been stuck with hyperbolic three manifolds and understanding just these cohomological. That's what this talks about. And there's no holomorphic structure on hyperbolic three space. Great interest of Mark Goreski. Twice here, right? Yeah. Hey, Mark. You hear me? You hear me, right? Just checking.
Right, as Peter mentioned that the great difference is that in the imaginary quadratic case, the locally symmetric space associated to that group does not have an algebraic structure. It's not even a complex manifold. And so another very different phenomenon.
Push this on the top and then push that one. So
Oh, I see.
that's the only way to do that.
Yeah, I'll do that next time. Actually, in this in the imaginary quadratic case, because the only interesting case is K1 equals to K2, then I will just use SKK or SK to denote this space. And unlike the real situation, the dimension of this space does not grow quadratically. Okay, I'll shift. So now I will shift to the idealic language. And I'll tell you how to interpret this space in terms of cohomology. So I'll use KF to denote a compact open subgroup of SL2AF infinity. It's a finite level subgroup. So this level subgroup can recover the congruent subgroup gamma by intersecting with SL2F. We consider the following locally symmetric space.
Wait, what's the meaning of this lowercase f?
Meaning it's short for finite.
That's infinite part.
Sorry.
But that's in the infinite part of this SL2.
So this is AF away from infinity. So
Lowercase subscript means you keep it. Uppercase subscript means you get rid of it.
yes, yeah,
Okay, so you're talking about finite on that.
The lower,
yeah, finite.
Okay, good.
not uppercase, lower.
Sorry. So the locally symmetric space is the following associated to this level KF is the following double quotient. And in the case of imaginary projective space, this is arithmetic hyperbolic spring manifold.
Yeah, he's earned his right to talk in our seminar. Just has to say.
Yeah. So with a universal cover identified with hyperbolic three space. And now we consider a representation of SL2C. Which I denote as WK. This is same Hilbert. Yeah, so I forgot to say that K is an even integer. It is a holomorphic representation tensors with its anti-holomorphic part. And they should have the same index. And this representation descends to a local system on our hyperbolic three manifold. So now we can interpret the space SKK gamma in terms of cohomology. So this is the consequence of Eichler-Shimura isomorphism.
I have a very naive question. In your definition of YKF, why is there an SL2C?
YKF.
What happens if you?
Because F is imaginary quadratic, so F infinity is identified with C.
It's just finite dimensional representation.
I guess that's the whole analysis.
Yeah,
Oh, I see. Oh, of course. Okay.
Yeah.
Yeah, this is a whole SL2 AF.
Okay.
So you can compute SKK in terms of the complex supported or cuspidal cohomology of YK. With this local system WK. So I will discuss the how to analyze the growth of the right-hand side in terms of the growth of left-hand side.
And presumably the two groups themselves are isomorphic through GK cohomology or something.
Which two groups?
The group H1 compact support and the group SKK are actually canonically isomorphic.
No, actually, so this a similar formula holds true for general number fields, but they differ from a power of 2.
And he's asking, you've got the dimensions are equal. He's saying the groups are the same.
Yeah. No, I think the group are not the same. Only the dimension are equal in this, at least in this situation. Yeah, so in general, the dimension differs by a power of 2 depending on the defect of the group. That's a result of harder, I think. Yeah.
I'm not sure. I don't remember. Did you ever tell us the definition of SKK of gamma? I would have thought this would basically be that definition because you need to use the C symmetric powers and define this local system.
That's right. That's right. You can define it. You can define this space in terms of this, but there are some other definition. I think, yeah. But for the purpose of this talk, you can just take this as a definition. But it can be the multiplicity of the infinity representation at infinity in the space of cuspidal functions, cuspidal automorphic functions. Yeah, I haven't defined that space, but
right. My question is, like, if you say that the two spaces are different, I can't imagine what the definition of SKK gamma is, other than what you wrote. But
yeah, I think you can take. There's another definition. It's like it is defined to be the multiplicity of the infinity type in the space of cuspidal automorphic forms. But yeah, there's another definition, but I haven't defined it, so we can take this as a definition actually.
Okay, thank you.
Yeah, good question. Thanks.
So this SKK is like a smaller subclass then than all the mass forms of that space.
If you think of it in terms of the second thing you were describing, yeah, these are a specific representation of unitary representation of SL2C, which is in the unitary dual, and it's a multiplicity of that exact guy.
Yeah, thanks.
And that's General Borel. Voila. But these are all cohomological.
Yeah. So we have some conjecture for the asymptotic behavior of the space SKK. I've said that it grows. It doesn't grow quadratically. So I will assume for the rest of my talk, F is an imaginary quadratic field. So the conjecture is that it observes that there exists a constant C depending only on the level such that this dimension is upper bounded by C times K. It's upper bounded linearly. Actually, this conjecture is supported by experimental data of Finis, Grauer, and Tyrrell. Yeah, Peter told me that they gave a talk maybe over 10 years ago precisely at this room.
That board.
Yeah.
I think the conjecture is actually a bit stronger. It's that
yeah.
when K is large, everything is base change, and then there's only fun. Then eventually there's nothing. I think.
Yeah,
I don't know if I believe that part.
Yeah, but that part I cannot prove, and I don't know if that's even true.
So we don't have a asymptotic.
This is an upper bound first.
I have an upper bounds. Yeah.
But then.
But in general, we don't expect some lower bound.
Yes, another point I haven't mentioned, I forgot to mention is that, yeah, there definitely, we don't have any knowledge of concrete formula of these days. And even you consider, so if you consider, for example, Euler characteristic, they all vanish, unlike the real situation.
Doesn't the base change give you lower bounds?
Yes, exactly. Yes. I forgot to mention that as well. Yeah, another observation is that this upper bound is sharp in the sense that many situations, basically you can lower bounded by the base change of classical elliptic modular forms, and that grows linearly. So the lower bound is actually a linear bound as well. And so there are some other evidence of this conjecture by Caligari-Mazur. They compute like so-called Hida family in terms of Galois deformation theory. And also supported this conjecture. And another remark is that there's a trivial upper bound to bound that space, and a trivial upper bound would be a quadratic bound. Because the dimension of WK is quadratic in terms of K.
Can improve that with the log denominator.
Yes, I will say that now.
That anything analysis gives you.
Yeah. Yeah, actually, the first non-trivial bound is given by analytic methods, use of trace formula. Finis, Gravo, and Tyrrell, besides providing experimental data, they also done some theoretical work, and they established a log K saving bound to the trivial bound. And so concretely, we bound this space. By K square over log K. So you can see this is a small improvement, but already requires very non-trivial tools using trace formula.
If I may say something, because I think a lot of people have thought about the Betti numbers as you vary the congruence group and you ask about the first bit, the harmonic one forms. And there, it's not. So what they're conjecturing here is that in the K aspect, there's obviously these base change ones, which are the same order of magnitude. And then they're saying that actually after a while, there's nothing new that can occur. But in the N aspect, we know that's obviously different because all sorts of conjectures of certain automorphic forms have to capture that. So the K aspect is the feature that it wants to not pick up anything new. And that's what you're not quite proving, but you're getting the right order of magnitude. And in the Betti number aspect, we know nothing like this.
Yeah, actually, I will discuss that connection.
In the N aspect, yeah.
N aspect. I think our method is related to the method Caligari-Hamilton proves in the N aspect.
Yeah. Okay.
Yeah, and so next I will discuss this this conceptual conceptual breakthrough by Peter's doctoral student Simon Marshall, which leads to a first power saving bound. So Marshall was able to improve this bound by a power. And the power he improved is k to the 5/3 plus epsilon for any small epsilon. And his very noted, remarkably, his method is related to the n aspect, I think, estimate using Emerton's completed homology. Yeah, any questions? Sorry?
Oh, that's a lowercase k, right? So it's
I'm sorry. So this is I read it too big.
That's from
okay.
short by.
Yeah. And his method is essentially, I think, algebraic.
Oh, yes.
Yeah. Yeah.
Well, it's Iwasawa theoretic.
Right. It was also. And later on, Marshall's bound was improved. So Marshall used characteristic P representation theory of, for example, SL2QP, so Yongquan Wu improved the Simon's bound, and his paper was recently published. Approved a better power saving bound. And the bound K got is K to the 3/2 plus epsilon. So I would say Yongquan followed the Simon Marshall strategy, but his the local statement is the strongest in the sense of so if you use Simon's method and you wish to prove a sharpest bound, I think the sharpest index you get is 3/2. And he so he uses techniques develops from some deep techniques to do from deformation theory of or P representation of SL2QP. These are some techniques developed from the so-called p-adic local Langlands program studied by the French schools. Okay. So today I will prove this conjecture. That we can sharply upper bound this space. So a few words that we do not need epsilon weighting as well.
He's great. Well, that's impressive. Yeah. It means there's no combinatorial analysis anymore.
Yeah.
Not only does he get the right exponent, but he does.
So to explain my proof, I will recall some notions, relevant notions.
Actually, I have
Sure.
maybe Alan Reed as an answer. If you take hyperbolic three manifolds and make these representations and you're not congruent, do you know if these, you know anything about these, Alan?
I don't, Peter, no.
You only looked at the Betty numbers?
Sorry,
Yeah,
what
that's
is
a
it?
good question. I think the cohomology that that statement for cohomology.
The question was, this is a very congruent statement and the proof that you, so what this is saying is a remarkable thing. It's saying a certain representation never wants to appear unless there's a good reason for it. Meaning it's a base change. And otherwise, the strongest conjectures, after a while, when K is large, you'll never see it. They'll never get excited. In principle, you could have it there, it's unitary, but it never appears. And he's almost proving that in this case. But if it's very arithmetic, this statement. So if the hyperbolic three manifold is non-congruent or non-arithmetic, maybe people know how to construct growth rates which are the log will be true in general. That's a Bianchi-Schramm convergence feature. But whether you can improve the exponent just from hyperbolic geometry may be false. So with the Betty numbers, that's definitely false. You can make them grow.
Right.
That's a very good remark, because I think the cohomology statement I gave is of interest of topologists, maybe,
yeah, right.
But that's only for congruent subgroup, but not crucially relies on that condition. If I remove that condition, I have no idea what's going on. Yeah.
I mean, the Betty number thing is Egel's big achievement, that you can always switch on the Betty number with some finite cover. That's this famous conjecture, but that was not even known in the arithmetic case. In general.
It was known for the Bianchi group case for kind of trivial reasons.
Yeah, but not for those very special arithmetic ones that you and I know so well, and Alex.
So I will recall Emerton's completed homology. So we pick a prime P that which splits in F. And I ramified.
Okay, so in your proof, K is going to infinity. This P is an auxiliary prime, which
Yes.
you choose with some property.
Yeah, this P is an auxiliary prime. I choose which splits in F and I ramified in KF. I will, so let G be a compact open p-adic group, congruent subgroup. So sorry, it's p-adic open subgroup of SL2FP. It is a compact p-adic group, and this K upper P is a tame level. So Emerton defines the completed homology as the following double limits. So first I take limits over small open subgroups in G, and you consider the usual cohomology of the locally symmetric space of level K lower P times K upper P. So this K lower P is a shrinking level you want to exhaust, and then you take a limit over the torsion coefficient with sufficiently large P power, and it's defined to be this abstract double limits, and then I want to work in characteristic P, so I invert P. And it has many good properties. I want to list a few. So this completed homology are admissible in the sense that they are finally generated modules over a number theoretic range. This range is so-called the Iwasawa algebra, and so this is defined. I first defined CP double bracket G to be just limit over the limit over the finite group range. Then I invert P. And this is a Noetherian QP algebra. Second is this completed homology of a torsion torsion modules over these Iwasawa algebras. That's because the Lie group SL2C does not admit a discrete series. And this arrow is proved by Calgary-Emerton. Actually, they use this property to prove many level growth in terms of the level, not the weight aspect.
That, again, in the log, in the k squared, the log in the denominator is exactly the feature that there's no discrete series.
Right. Yes. Somehow analytic method proves provides a log.
Gets you just off a line.
Right.
It's a bit like Deline's proof of the Weil conjectures.
Right.
The Weil conjectures, you know the purity, but you have to get first pass the line 1. And he rederives Adamar de la Vallée Poussin just to get that past that step. But then you got all this algebra going for you.
So, I proved that degree 1 theory in terms of log k, degree 1 over log k. Yes, that's a trick.
Can I ask a question?
Sure.
What does it mean? You've tensored with QP, so what does R torsion mean?
Oh yeah, so this torsion is, for example, if I choose I have a module, and for any, maybe I forgot to mention this ring is an integral domain. It's a non-commutative integral domain, and torsion means that there is this non-zero R in this ring, in this integral domain, which kills for any M, which kills M. That's a good question. And lastly, we need to recover the usual homology in terms using completed homology, and so there is a spectral sequence for recovering the usual homology. So at E2 page, it is ice homology of the J's completed homology. Answer with WK. And this should convert to I plus J's usual homology of the locally symmetric space with level G times K, KP, K upper P, and so with local system WK. And this spectral sequence is a source which provides us the desired upper bound. So you see that I can bound this usual homology in terms of all the sum of the E2 terms, all possible sums. So now it suffices for me to prove a local statement ignoring these arithmetic properties of this completed homology, and I will state my local statement.
Sorry, can I ask another?
Yeah, sure.
What is WK here? What is it a representation?
Yeah, sure. So
it's just the same thing where you took.
right, but now I shift from academia place to p-adic place, so I'd better say another time. For example, you can take this is, yeah, I also want to simplify my notation. I use K here. And because my p-adic place auxiliary P is split, and this receives, I would say it receives action of SL2ZP times SL2ZP. So and G is a subgroup I choose inside of this. So it is a representation of G.
But in the limit, then we're back to our normal WK at infinity.
Yes,
Like,
yes. This you can switch the characteristic in the usual cohomology. You can switch from QP to C here for WK. Yeah, that's good comment. Yeah.
So this is where the shift happens.
Yes, for the last step. Yeah.
SimK of what?
So the sim is the standard representation of SL2ZP, right? Two-dimensional standard representation, and you can consider this is symmetric power. Yeah. So yeah, actually now I assume I will take G to be a particular open subgroup inside. These are elements congruent to identity mod P. And so it is two copy of that. So this G now is a pro-P group. It's and with and in the sense that it's uniform, but I probably won't explain what does that mean. But these groups are studied by Lazard, and they have many good algebraic properties. So the local statement I prove is the following. I can bound all the homology for torsion modules of these groups, or of this group G. For any finally generated torsion Iwasawa modules.
Again, the trivial bound is K squared, right?
Yes, yes, yes. The trivial bound is okay as well. But now I provide degree 1 stable bound for any torsion module. Yeah, and I would say if you remove the torsionist, it would the best you can hope is a quadratic bound. Yeah, the torsionist is essential.
The intermediate step to prove the previous one.
Sorry?
Is this the intermediate step to prove the first?
So using this result, and you apply to this, and every term in the right hand side will be bounded linearly. Yes, that's the strategy. Yeah.
In Simon's result, does it?
Simon's result is not this result. Simon's result is a characteristic P result. My local result is a characteristic 0 result.
Sure.
Yeah.
But is he, okay,
Yeah, that's where the difference happens.
but he's still trying to bound these.
Yes, this
like
his
similar.
he still tries to bound somehow bound this group,
Sure.
but his result he used more P reduction. Yeah, yeah, but I think using more P reduction, you lose some information. That's why I studied this. Yeah, probably I won't have much time to explain how do I get this local result. I will just sketch my rest of the proof. So my strategy is to linearize this problem because we know this G is a highly non-commutative group. We try to linearize it by passing our problem into to a Lie algebra problem because Lie algebra is more linearized. And this was this was possible by some work, previous work, for example, of Lazard. Lazard associate for uniform for P group. We can associate ZP Lie algebra to it. I call it G0. And here the G0 is just SL2, but it is the algebra SL2. And another very important ingredient I use is by consider, sorry, I will define the completed universal enveloping algebra.
This Lie algebra. For the Lie algebra. This universal enveloping algebra.
Yes, it's a variant of the usual universal enveloping algebra, but it's P completed. So I defined it to be just the usual completion of the p-adic completion of the ZP universal enveloping algebra of this ZP Lie algebra. And then with P inverted. Then I invert P. Yeah, another point is that although I invert P every time in this talk, but in my proof, I still need to use this integral structure. And so there is some so-called micro localization. By article and vastly. they construct a map of which is a flat ring extension from the Iwasawa algebra to this completed universal enveloping algebra. This is a flat ring extension. So using this map, I can linearize my problem.
Is it a homomorphism or is it?
Yes, it's an algebraic homomorphism.
It is
A homomorphism between Noetherian QP-Banach algebras. And it is flat.
Do they say why they call it micro-local?
Because I think
Sounds like quantum mechanics or analysis.
yeah, I think it's related. Well, there are several reasons. So the formal construction is by first using a non-commutative localization, then do some completion. Another reason is that I think in representation theory, if you pass to, so the algebra is an infinitesimal concept. I think so. That's how I understand the term, but I don't know why they call it this name. They probably have better reasons. Okay,
Their discussion's probably not for this G, right? It's much more general.
yeah, it's much more general. Yes.
What do you mean much more general? No, I think it must be a uniform P group, no?
It must be a uniform P
not just
not restricted to SL2 case.
That's
Can be higher rank group.
I mean, I don't know this specific paper, but what I know that if you take a uniform P group, you can really define, you can really see the Lie algebra and
Yes.
inside it, you can really identify the group with the Lie algebra and by defining the operation there and vice versa. So it's really like you can think of it.
But that
Like
the
the
question
exponential and the logarithmic map in some sense are kind of the identity when you change the product. It's something which is really delicate, but just for uniform P group. If it's analytic P group, but not uniform, then it's not really working.
he's not arguing with you. He just the question was much more trivial. Is it restricted to SL2? And the answer is no.
I see. No, okay, yeah, but it's yeah.
And you say, is this a canonical map? Like, is it characterized by some properties or?
Yes, it is a canonical map, but I don't have time to illustrate on that.
Okay, thank you.
Yeah.
So he's here in Princeton, and you should get the information from him. Yeah, this is that's what I wanted. I wanted people to be familiar with this work.
I'm happy to be better. So another important reason for us to pass our problem to the algebra level is because I prove this following comparison theorem. Yeah, I probably, sorry, I haven't say. So we start from a finite generated Iwasawa module. Then we can linearize it to consider the base change over the micro-localization map. Then I prove a comparison for the algebraic quotients of M hat. So that's MK tutor and M hat tutor. M hat K be respectively the maximum WK quotient of quotients of these two modules. Then there's comparison. There's isomorphism identifying these two WK quotients. This is somehow this space represents a multiplicity of the algebraic representation inside this very abstract finally generated modules. I think I will stop here and take any questions, if any. Yeah.
All right. So I think there may be a lot of questions. Should we start with the Zoom people? Alex, got any questions?
No. I just wanted to. I will look at that paper. I didn't know about that paper, though. I kind of guess where it comes from.
All right. I have a question. Sure. So in the Caligari and Emerton, they kind of represent this, and there's a sort of a variety. It's three-dimensional.
Yeah.
And this whole gaining of a power is decreasing where these points lie on the variety. Do you actually get involved in that, or?
Yes. Yes. So there's a notion of canonical dimension for the Banach representations, or Galfond-Kirov dimensions if you pass to the algebra level. And so I think I use the fact that this dimension is an integer. So if I know its torsion, it must decrease at least one. And that's how I got this degree 1 system down. And so do Caligari and Emerton. Yeah.
But you gaining, well, and Marshall also used that somewhere.
Yeah, Marshall also used somewhere, but he wants to prove a characteristic P.
Yeah, okay, so the reason he should have gained 1 if he was working in characteristic 0 in some sense, is that what you're saying?
Yes, I think characteristic P, if you pass your characteristic P due to reduction, you lose information. Yeah. I think. Okay,
I think that one question that I have here, which I think many people will be interested in. So if you go, let n vary, if you take congruent subgroups P to the K, let K vary, then Caligari and Emerton prove power saving.
Yes.
But not, the exponent's also incorrect, right? Conjecture is probably wrong, do you know?
Sorry, can you say that again?
If you're doing the Betty number.
Yes.
Same setup.
Yeah.
We're not varying K, we're varying the level.
Yes.
And the level is P to the K, so we set up for Iwasawa theory.
Yes.
Then they prove the power saving.
Yes.
For the Betty number.
Right.
Their power also must, again, there you can ask what's sharp.
Oh, I see.
You're not
I think, yeah, that's a good question. I think in general, that's definitely not available at the moment because.
And it may not be true there.
Right, it may not be true. And that's because in general, a group can have greater than 1. The defect can be greater than 1, and so we don't know any case that is proved. So that's related to a so-called I think the Caligari-Emerson's conjecture. so-called non-abelian Leopold conjecture.
Yeah.
And for groups which have defects, at least 2, we don't know anything about that. But for groups which admits defect being exactly 1, we know those conjecture.
Here SL2C has defect.
Yeah, the SL2C has defect exactly 1.
Yeah.
Yeah. Yeah, and for groups, I think for groups with defect at least 2, I think Calgary Amazon's papers, their bound is may not be sharp.
Yeah.
So I think it's related to what Peter said. So
sure.
Does your results establish certain case of the Sarnak-Shih conjecture?
No,
I can answer that. He's doing much more. The conjecture that we have, which Matilda has got the sharpest results on, that involves non-tempered representations, and they're supposed to not be there unless there's some functorial transfer. These are all tempered. And so tempered are allowed to be as rich as possible, but actually not. That's the amazing thing. So these are all tempered.
Yeah, these are all tempered.
So ours is about non-tempered, and then you get a power saving, but from another source. So this is kind of this is really an interesting challenge. And it's basically the question of when do you have cohomology? And somehow in the n aspect, and maybe in this aspect, in the arithmetic case, you only have cohomology if sort of there's some algebraic conjecture that's like the Shimura Taniyama says it better be there, and then it switch itself on. Doesn't want to switch on. That's what he's proving. It's remarkable.
Thanks.
Yeah, I think it's really interesting. I think we would probably want to see more details, but I suggest people find them out from Weibo directly, since it is lunchtime. Let me just announce that next week we don't have a seminar. There's a workshop, and the week after will be the final seminar. It will be in class, in person, and it'll be Alex Gumbert. And I encourage you all to come for that. And that'll be the last lecture of the seminar for the year. And let's thank, unless somebody has so many questions there, then let's thank Weibo for a lovely, it's a very beautiful result. Thank you.
Thanks.